case of convolution, it is the convolution between rectangular and step signal. See, the convolution between rectangular and step signal means one of the signals is finite and another signal is infinite. In all the previous problems, both the signals were finite. But here one of the signals is finite and the another signal is infinite. The procedure remains the same, only the number of cases changes. The number of cases through which you have computed the convolution, that changes. So then how to take the cases here? First, before I get into the problem, let me just take an example. See here, this is one finite signal, this is also finite, this is also finite, this is also finite. Now assume that we need to compute the convolution of this finite signal with this infinite signal. So whenever it is between finite and infinite, we should always time reverse the infinite signal. Then the problem becomes easier. You can do the reverse also. You can reflect the finite signal also, no problem. But it will be easier. If you reflect the infinite signal, then it is easier. So how to consider the cases? Suppose if you want to compute the convolution between this and this, then this is the infinite signal. First reverse this, then shift this. So starting becomes here, the starting. So now what we have to do is, convolution means wherever the amplitude changes. Before the amplitude change, we should consider one case, and after the amplitude change, we should consider another case. See here in this problem, the amplitude changes here and the amplitude changes here. So the first case of convolution is the beginning of the reversed signal before this amplitude change, means this will be case 1, and the beginning of the reversed signal is after the amplitude change, means this becomes second case. Then the beginning of the signal before the second amplitude change, this is the second amplitude change now, before this means here only. Then after this amplitude change means this. So see here these two are being the same cases, these two are same cases now, so it adds to case 2 and this is the third case. Okay, so here in general what we can say is, here we will encounter 3 cases, one before, in between and after. And same with here though the amplitude is continuously changing but the expression remains the same. Whenever the amplitude expression changes, we have to stop over there. Okay, so here the amplitude expression is same throughout, so no problem. Here one amplitude change, another amplitude change. So first case before this, second case between this, after this. Okay, then here in this case it's very interesting. Here also it is same as this. Here one amplitude change, here another amplitude change. In between the amplitude expression is same. So before, after, this being the same, this 2 and 3 are same. Now, so this adds up to only one case, so second case, and this is the third case. Whereas here, see the amplitude expression changes here, the amplitude expression changes here, and the amplitude expression changes here, right? So one case before this amplitude, another case after this amplitude change, next case before this amplitude change, after this amplitude change, before this amplitude change, after this amplitude change. These two being the same cases, you can club it together. These two are same, so club it together. So we have 1, 2, 3, 4 cases here. Okay, now we will get into the problem. So compute the convolution of y of t is e power minus 2t, u of t minus 3 and u of t minus 1. Now see here, u of t minus 1 is the infinite signal. Let us take it as h of t, and u of t minus 3 means the signal exists from 0 to 3. To that the amplitude e of minus 2t is multiplied. E of minus 2t means it is decaying signal. It is decaying exponential, right? So decaying exponential in the interval 0 to 3. It looks like this. Your x of tau look like this. H of tau. Always time reverse the infinite signal. Reverse it. Add t to this. So t minus 1. After this the procedure is exactly same. First case, see here the amplitude changes here and here. That's all. Means before this, between this, after this. That's all. So first case t minus 1 less than 0 means you are shifting it such that the beginning of this is less than 0. T minus 1 less than 0. T minus 1 is less than 0 means t is less than 1. So now it looks like this. No overlapping. So the convolution is 0. Next you should move this h of t minus tau such that t minus 1 it will be in between 0 to 3 means in between the finite signal. So now see here it looks like this. So now the region of overlapping is from 0 to t minus 1. behind 0 x of tau is 0, after t minus 1 h of t minus tau is 0. So only from 0 to t minus 1 both the signals exist. Region of overlapping means the time interval during which both the signals exist. Okay, so the region of overlapping is 0 to t minus 1. Compute the convolution between 0 to t minus 1. So the second interval is t minus 1 in between 0 to 3. Shift this minus 1 to either side. So the interval will be 1 to 4. So convolution is to be computed from 0 to t minus 1. X of tau into h of t minus tau. The amplitude of x of t is e power minus 2t. X of t's amplitude is e power minus 2t. So x of tau's amplitude is e power minus 2 tau. The amplitude of h of t minus tau is 1. So 1, integrate it, you will get this result. The third case is you are shifting this h of t minus tau such that the starting it is after 3, means after the ending of the signal. That is t minus 1 is greater than 3. If t minus 1 is greater than 3, t has to be greater than 4. Now see here, the complete signal, the complete finite signal is covered by this infinite signal. So now the region of overlapping is 0 to 3. Okay, so x of tau into h of, now compute the convolution for 0 to 3 and you will get this answer. And try to do this problem. Here u of t is infinite, so try to reflect it or take it as h of t, no problem, and take it as x of t. Try to do this. It is u, okay, it is u of t plus 1, u of t minus 1, and solve it and send it to me by evening or tomorrow morning. Okay, tomorrow I'll just upload one more video. Okay.